Not going to do it. All right, people. So I'm not going to record lectures, at least not for the first few weeks. There's administrative and technical problems with Zoom. Like I said, I won't use Blackboard. I tried using that. It's a nightmare. It's not deterministic. It just does weird things every once in a while. I can't have that. You guys can all record. You have my permission. You can record these lectures. I can't stop you from doing it. You can do whatever you want if you're working from a virtual box. Most of you know that. All right.
Apparently, we need to ask your permission.
Well, no, not really. I'm giving you my permission.
Oh, I guess like just using the record button.
You can do whatever you want. You go ahead and record all you want. All right. I'll try and behave. I'll try and behave myself. Also, I want these lectures not to be very interactive. All right. We'll just save that for office hours. My office hours will be just continuing on afterwards. You're welcome to stick around. And that's when I'll really, we'll your concerns, or in email, or even in telephone conversations. So I find that infinitely preferable to recording. A lot of my peers, they're not only going to record them, but they're going to edit them and turn them into productions. And I find that that's nothing compared to actual discussions over Zoom, say, or particular face-to-face. So that's the way it's going to be in my class this summer. We'll just, if I can record eventually, I'll do it because I think a lot of you would like that. Any questions about that? I guess not. That's us right there. Compute 409, that's when we'll be meeting. That's where we're not going to be meeting. And this is when the final exam is. It's August 17th. Nothing new there. That's me. And you probably already read that. No big deal. But the big thing is that I'm heading the academic program for quantum computing with physics, mathematics, and engineering. So it's a really big deal. Plus, we're starting a Quantum Algorithms Institute. That's just politics. Why it's in Surrey is just politics. And so there you have it. By the way, I'm not going to do this, and make it full screen because the pictures texture, this is a very computing science-based book, hence we call it applied. Algorithms, that's what we want to spend a lot of time on. Different kinds of programming languages, well, we're sort of at the assembly level here. And then, of course, a bit of theoretical computer science, very important. Cryptography, the reason for the funding. I think you could probably understand that quantum computing is all about cryptography. As far as the funding goes, it's of national strategic importance. A bit of information theory, talking about the hardware as well. That third book right here, this is the standard book that's used for this course, but from physics departments. I want you to get that one, all right? So the first book and this one, you can find this online. And if you have trouble getting it, I'll send you the second chapter. Because it's actually section 2.1 that I want you to know. Okay, so for example, fundamental concepts, quantum computation, that's half the book right there. You don't even have to worry about that half if you were learning from this book, the entire course. But that's the only part I want you to know, section 2.1. I will send that out to you, all right? I'll just send that out so you don't have to make sure. Let me write that down. Okay. So, my power cord's failing me. Oh, you little twerp. Oh, God, look at that. There we go. This is a fourth book. This is about quantum computing virtual machines, all right? And so you can go to IBM and get a hold of this thing. It's the programming language QSkit, which is based on Python. Very easy. This is where we're headed. There's a second one here. It's from Rigetti. Rigetti is one of the major quantum computing industries. It's down in California. And this is an important one because one of their software engineers, mathematicians really, has put out this beautiful paper called the Practical Quantum Instruction Set Architecture. This one right here. That's this. You've got to get that as well. And this slide here gives you our basic summary of what's expected in this course, all right? I want you to be able to write simple quantum computing algorithms using one of these languages, Python-based languages. They're very simple to use. A lot better than the quantum computing circuits that you'll be learning first. That would be like programming in binary back in 1940. You also have to be able to understand this paper. This is your litmus test for the course. By the end of the course, you should be able to read this paper with a moderate amount of difficulty. It's just a goal that I've set. And so you should start looking at it. And finally, in order to do that, you have to have some proficiency in the area of advanced linear algebra. We'll describe what that is. When will we do that? Next week. Any questions so far? Anything at all? Huh, nobody. Huh? Let me see. Let me unmute you and see what happens. Unmute. Any questions?
No.
No, sir.
Negative.
Yes. Okay, just one at a time. Okay, never mind. I'm muting all of you. It's just a cluster. Okay, if somebody wants to ask a question, just say so or just talk. I'm not hearing anything. Okay. Maybe I should unmute you again. I'd not forget it. Okay, let's just keep going. Let's keep going. This is very important. Don't forget about this PowerPoint. This is, better than any web page. Okay, I'm not going to set up a web page for this course. This is your guide to the course. This is a very good resource right here. You could go there anytime you want. You don't have to, but this is an excellent source for coming up with projects. Okay, get familiar with Qiskit and PyQuil, and then you can come up with projects for this. The end of the term, you have to actually make a presentation for the class in groups. Okay, like I did with 376, that type of stuff. Here's another outstanding resource. All right, Pearce, you're here. Nice to see you.
Yes, you too.
Very good, sir.
Thanks.
Okay. Okay. From Los Alamos, we have this wonderful paper, Quantum Algorithm Implementation for Beginners. This is an outstanding paper. You're not required. Again, what you're required, I'll show you at the end what you're required for grading, okay? These are really nice additional resources. Caltech is, of course, the center of physics in the world, and Pruskel is regarded as the central figure in quantum computing from the physics side. So if you want to look at his notes, that's fine. I won't make you responsible. If you don't know who Richard Feynman is, then you should go back to high school. Just kidding. He's the inventor. He's a Nobel Prize winner from Caltech. His Feynman lectures on physics, in particular the third volume, are as good as they get for quantum computing, or no, for quantum physics. MIT OpenCourseWare, there's a course for almost anything. There's a person from Austin, Texas, Scott Aronson. He's my favorite personage in quantum computing. Any of his notes are great. De Wolf, he's from Holland. He's one of the pioneers as well. Fantastic set of notes that he's got. And then, of course, there's Microsoft Quantum Documentation, which is absolutely excellent. It really is. And then there's a website called Quantum Computing Glossary, again, from Microsoft. These are good things to look at. There's some good videos. Those of you that are more video inclined, we're actually going to be responsible for this video right here. Quantum Computing for Computing Scientists. Sorry, computer scientists. That is taught by a guy that looks like a frat boy, but he's outstanding. He's really good. I shouldn't have said that, but I did. And when we're learning the mathematics and taking a first sort of a simple run through, we'll be depending on, I'll show you his slides, but you should look at it beforehand. That is about an hour-and-a-half lecture that was given in Microsoft, I don't know, about maybe 7 years ago, and it's outstanding. It's really good. You're all urged to look at it beforehand. This individual here from CMU, these lectures he gives are outstanding, but this is just so you can have a look. Michael Nielsen, he's one of the authors of the third book, the one from which the mathematics section 2.1 will rely on. So that's excellent. And then anything from Scott Aronson. There's Scott Aronson right there. Hopefully we might have him here for a guest lecture, but it'll be virtual. One of our faculty members knows him well, and so hopefully we can talk him into it. Here, I like to use icons. And so you'll see this icon whenever there's an important side note. Whenever I have to play a video for you, it's here. Videos are there to sort of intersperse my boring lecture style with somebody else's. That's a suggested video. That is something I'm sending out to you. You have to read. That means for your information. It's not required. But of all of these, that's the only one you have to worry about. Everybody good? So if you see that, that means I'm going to send you something, or you look at the link and something magic happens. You get the paper and you have to read it. All right? Also, I always put my references for slides in the lower left-hand corner. You know, practically see one all the time. If there's even a remote reference I've made to somebody else's material, I'll put that link there for your information. Anybody know what the rabbit hole is? There's a lot of rabbit holes here. Okay, down the rabbit hole. It's from this story, Alice in Wonderland, right? It's a metaphor for being transported somewhere to a wonderful or troubling place. And quantum computing is full of that. So every once in a while, you'll see a slide like this, and we're going to take an excursion into the strange world of quantum mechanics, or maybe mathematics. So, given that this is our textbook, this is going to be our guide for the syllabus. And so from this book, it says we recommend starting with the opening 2 chapters, which are about the basics of quantum physics, you know, the entanglement, superposition. We'll define those things shortly. Then jump to the mathematics section, which is all of part 3, which is 150 pages. That's why I'm going to the 3rd book, because there's only about 20 pages there, and it's dense and it's good enough, but you can always go to part 3 of this textbook here if you really want the gory details. It's a really, really great reference, but it's just too long-winded. So I'm not going to make you read part 3 of this book. We'll work on section 2.1 of your 3rd book by Michelson and this right here. That's the one we're going to look at right here for the mathematics section. So replace part 3 of your textbook with section 2.1 of that, which I will send to you. Okay, well, this is looking pretty good, people. So given that, then all the chapters are coming out of this book, except for in week 2, that's next week, section 2.1 of Nielsen and Chang, which is that book. So what are we going to do this week is a broad introduction. Quantum mechanics, quantum computing, quantum information. What is information, in fact? And kind of an introduction to quantum algorithms. Can't do much yet. So it's the first assignment that's going to get you to think about what it is. And I'm going to give it to you on Thursday. Your first assignment's on Thursday. That's asking a fair bit from you, but we got to get into it right away. Don't worry. The first half of this course, there's a lot of stuff here. I'm going to drown you. You're going to be out in deep water. It gets better by the second half. It'll be more fun in the second half. You see that? Say yes.
I just have a question about the assignment.
Okay, go ahead.
Just to be clear, it's assigned on Thursday, not due on Thursday.
It's due yesterday. Of course. It's going to be 2 weeks. You'll have 2 weeks. I never give assignments. Rarely I give assignments that are due in 1 week. But certainly, no, you've got 2 weeks to do this. And it's forcing you to really think about what a quantum algorithm is. Everything about quantum, people, is fundamentally different from anything you've learned already. The notation, the mathematics, the way it's implemented. They try to make it, piggyback on classical computing, but it's very challenging, let me tell you. And so you think about it this way: we're at this stage right now of quantum computing where we've just developed second generation, assembly code, but we still haven't got the actual computer working. That's where we're at right now. In fact, some people think it'll never happen. It will. It will. Just give it time. Qubits, qudits, block sphere representation, interesting theorems, Bell states, that's about entanglement. A very, there's different interpretations of quantum mechanics, 3 of them basically. The Dirac, Heisenberg, and Schrodinger picture, I'm not sure if anybody's familiar with that, doesn't matter. I'll make sure you know what you're responsible for. We're basically going to be using the Schrodinger approach, which is based on Schrodinger's equation, though you don't have to deal with partial differential equations, fortunately. We just need linear algebra. But that's the way it's executed. The Schrodinger equation is how quantum states evolve, even though you can't observe it directly. It's a very bizarre world. We'll talk about it on Thursday. The density matrix is an alternative formulation, but it's only for what's known as mixed states. Quantum circuit model, models of quantum computation, universal quantum gates, etc. All right. Here, this thing called the adiabatic theorem, that has to do with D-wave and their quantum annealing machines. We'll define all these things. In the 4th week, we'll talk about complexity theory. This is going to be pretty challenging. In fact, what I would like for this course is compute 309, I believe it is. 309 is computational complexity. I would love for that to be a prerequisite for this course, but I think the powers that be wouldn't let me do that. Might be too challenging. But this is where we're going to have, in the beginning of June, exact date. The exact date for our guest speakers will be June 4th. June 4th, that's a Thursday. We'll have 2 hours from 2 speakers from Qubit on quantum algorithms. It's right there, June 4th. So that should be very exciting. Now, here's a really exciting week. It's called Slack Week, and that's because I don't know quite how this is going to work. This is the first implementation, and so I might have to go over material that we're covering here, which is quite a bit. You might, understand the first 4 chapters of your textbook, including this section here, which in your textbook means all of part 3. That's a lot of material, a lot of concepts. It's a fair bit. Maybe I'm going to stretch this out into the 5th week. I'm pretty sure we can't cover this in 4 weeks, so that's why that's there. Excuse me. Then finally the midterm, and the midterm is going to be, I don't know, week afterwards, I suppose. Week 6, of course. What's going on here? How come I don't have it? Oh, there it is. The 16th. 409, the 16th. So you're going to have a 50-minute midterm, and I'll prepare you for it. Believe me, I'll prepare you for it. And then that same week, we'll talk about how to build these things. And then there's the second half of the course. We'll talk about that later. In fact, most of these things we'll actually be talking about in the first half of the course. So the second half is going to be mostly you working on and us discussing in sort of workshop-like sessions, your quantum computing algorithm assignment to your term project, which is going to be actually a lot of fun. The whole point of it is to actually have a good time, and let's see how that works out. So here you can keep track of what we've done by looking at the email archive and what's it called? Course Central. There it is right there. There was a time when I said LaTeX is required. I put in not required now. I can't ask that much of everybody. If you've taken 376 from me, I make you learn LaTeX there. This is where it really belongs, because LaTeX is a mathematics markup language. And those of you that don't know it, I urge you to learn it a little bit anyway. You can download this link right here, which has been graciously given by Professor Oskin from the University of Washington, just a couple 100 miles away. It's available to anybody, and it's basically his notes in LaTeX, and you can change them all you want. It's once you have that template, it's very easy. And so it's if you try and use If you try and use Word to do your assignments, I'd rather you just handwrite them. And when it comes to a lot of this advanced linear algebra, it's very difficult to do it with Word properly. LaTeX is the standard for anything that's mathematical physics. But I'm not going to force you to do it. That's not fair. Okay? And you can hand in assignments handwritten. I'm just going to make it that relaxed. Is that fair? Okay. Nobody's saying anything. Here's the breakdown: 15% for assignments, the midterm June 16th, 20%. Term project, 20%. That's a programming project, and you'll be giving a demonstration in front of the class with this Zoom feature. And then, of course, final exam. That's the breakdown. So you should organize yourselves into teams for the term project, no more than 5 people. And you should also be thinking about choosing a topic by the 3rd week. I think we'll have covered enough so that you'll be able to understand what to do with a quantum computer and what problems can be addressed and the kinds of problems that just aren't addressable. You know, for example, you all know what parallel computing is, right? You know, it's where you kind of like using a GPU. The GPU does things in a massively parallel way. It's like a matrix of processors, small little processors that are used, you know, for example, to manipulate an image, which is a square or rectangular array of pixels, and they don't depend on each other, and so you can do them individually. At the same time, if you have the same number of processors, well, there are certain kinds of problems that are not amenable to parallel processing like that. Because it has to be done in sequence. So the same thing can be said about quantum computing. There are some problems that are very amenable and some that aren't. So we'll figure that out. Okay, and here's a good place, again, to look for the kinds of problems that you could wake up, Steve, the kinds of problems amenable to this. So you can use Canvas to actually get your teams organized. And you can also create them with Zoom, and this tells you how to do it. Somebody sent me this, and I pasted it in there for you. And you should all go to sfu.zoom.us in order to use your SFU account for Zoom, which is all very new. That's what you should be doing. Okay?
Question here.
Yes.
So how long will we have before those teams are randomly created?
Well, I'd like you to, I don't know. If you don't create them yourself, I'll be forced to randomly create them, won't I?
Yeah, but do we have a deadline to?
Well, I mean, it's right here. It's right here in red. Okay. It should be finalized by the end of week 4.
Thank you.
Okay. So you got to begin to choose a topic starting no later than week 3 and to be finalized. And that sort of means that you've already got your teams organized. You should start organizing yourselves at least no later than the end of next week. You should have your teams organized. And those that are stragglers, I'll put you into teams. And we'll see what happens. Kind of like an experiment, right? Any other good questions? Well, then, let's move to this. So this is a summary of how to survive this course and survive it with a good grade and a good taste in your mouth. There's this required textbook. That's our guide. Between this and my PowerPoints, that's where I extract all material, testable material. I'll be very clear about what is examinable. For example, section 2.1 of the 3rd textbook, those mathematics sections, that's from this book right here. All of the answers are given to you. I've given you all the answers. There's about 50 problems, so I will be reasonable. I'll let you know the ones that I think you should work on. And after all, what is it? I'm basically saying you can just memorize the answers. And that's maybe not the best thing, but that's what I'm giving you so that you're relaxed in your fear of the high-level math that's required in here. But you're already expected in reality to have taken a course beforehand where you've mastered that in order to be in this course. So I think it's a fair trade-off that I just give you the solutions. Everybody okay with that? Just say yes. Nod. Do something.
Yes.
Thank you.
Yep.
Beautiful.
Sounds good.
Okay, so here I have this programming project as well. It's not going to be graded rigorously. Like I said, the second half of the course, I'm going to give you a break. You know what? I always do this with all my courses. I ramp everything down. I start big and then start ramping down because I find that most other instructors tend to ramp up. And so, everybody's stuck with too much to do at the end of the semester and it burns people out pretty quickly. I like this course to be more enjoyable. You have, more time to spend on your other courses as well, because they're pretty demanding by the end of the semester. That's just what I do. It's how I do it. Also, you notice the red background. Anytime you see that, that means, well, it's important. We're running out of time here. I got 15 minutes left. That's not bad. I don't think we have any holidays. All right. So we'll just be going straight through. You all know about this stuff. And here we go. You'll notice I'm standing right there. That's me right there. See that? This is us, and this is this course. And so it's very different, like I said. The notation's different. It's there's a lot of mathematics that and notation like Dirac's bracket notation, which is different. People like to just say, well, this qubit, that looks like this, and they don't know what they're talking about. You have to understand it. And the idea of bracket notation is steeped in high-level mathematics and Hilbert space theory, which we are going to master. Okay, so you'll see some advanced mathematics here, but you'll see partial differential equations, but you won't have to understand them completely. You're not going to have to reproduce them at all. Okay, so don't worry about that. Look, the big picture is going to be given to you, and so just stick with it. Don't be intimidated. And of course, the last sentence there. Here's a postscript for you. This is the first one. I've told you already that this course must succeed. I think I oversold the course to you people from 320. I kind of did a lot of this, and I'm not going to back down from that. If you stick with this course, you're going to make it through. Some of you are going to be, I don't know, way too intimidated by it, but just stick with it. I guarantee you I'll pull you through it. It'll make you more marketable out there, because this is going to be the next big, revolution of sorts. It'll be very, very important for the pharmaceutical field and for computer security. It's a huge thing. It really is. And in my opinion, it's going to happen for sure. Quantum computing will happen. It's just right now very difficult to see the big picture. There's a second post. Yes.
Okay. You mentioned a quantum computing certification. Will we be doing that at all?
Right. No. I didn't. I said that's what we'd like to have. We'd like to have some kind of a what do we call it? Yeah, certification or I can't remember what we call these things. But something eventually is going to be, not just for one course, we're having taken the 3 courses that we're designing. So there's a redesign of a second-year physics course that's been passed already that will be the prerequisite for this course. And all of that stuff isn't going to be ready by the end of this semester, obviously. You're not going to get anything for this except for credit for taking Compute 409. But eventually, hopefully within the next, I don't know, maybe a couple of years, maybe even less, there'll be some kind of a quantum certificate. I'm not sure how that's going to work. I wish I had more details for you, but
thank you.
That's more for the administrators. I'm not privy to a lot of that at this point. All I'm supposed to do is get this course running and then work on this graduate course. That's my end of it. So like I said here, Physics 285 is going to be the prerequisite for this course eventually. High-level terminology, hypothetical first course. What I'm trying to say with this sentence right here is you're supposed to have gotten into this course having mastered the proficiency, mathematics of this. And that's why I'm giving you the answers, okay? All solutions are provided for the problems in math. I'm not going to make you responsible for all of them, but just the basic kind of stuff, you'll see. And so stick with it, and with a little reasonable effort, you'll be fine. As far as the mathematics, the formal side of it. There's another part, and that's the understanding of quantum mechanics, like entanglement and things like that. It's very challenging. So always refer to this PowerPoint so that you know what's required of you. And all lectures will be emailed to you in PDF format. And here, we haven't got time today to look at this. I don't know how many people here have ever gone to Kyrgyzstan.
Yeah, I've heard of them.
Yeah, they're pretty famous on YouTube, I guess.
Yeah, they've got some nice videos. At least one of them's controversial, but if there's no controversy, what good are you? This is something you should all watch before Thursday. It's only 7 minutes long. The thing I don't like about Kyrgyzstan, like most videos and methods of teaching today, is, well, they're pretty infantilizing, making it all like a little children's story. But frankly, I can put up with it. In this case, their videos are good. So watch this for Thursday. And if there's any more questions, I'll take them right now, because that's the end of it today. People?
If we do wanted to get more into the maths, the PTEs, and yeah, will we have the resources to do so?
Absolutely.
Okay.
I've here, if you really want to get into the math, go to any of these right here, like especially Presko's notes on quantum physics, on quantum computing, I'm sorry. As far as the advanced mathematics goes, when we're in that section next week, I've got plenty of links for you, plenty of links. We don't no end to the amount of information that I'm supplying to you here. It's a good question. I'm glad that there's somebody that's interested in the formal side of this. Anybody else?
I had a quick question. If we were to record these lectures, would it be okay to have a private YouTube playlist to share among other students in the class?
I don't care.
Okay, cool.
You can do whatever you want. I don't like YouTube. It's addictive, but I'm sure that it'll be fine.
Thank you.
You have my permission to do anything legal.
Thank you so much.
You're welcome. Anyone else? I want to have a good semester. I want to enjoy this. I'm really excited about this. All I want from you is to stick with it and to give me a lot of constructive criticism, constructive advice and constructive criticism, please. That's what's necessary in order to make this a better course. So I'm counting on you people. You're my guinea pigs. All right. What do we have here? It says right here. I don't know. What does it say here? In return, okay, so you'll have to perform, but this course will be reasonable considering the amount and type of material involved. And here it says, in return, I expect honest constructive feedback for steering this course forward on top of what we have to deal with this COVID-19 nonsense. Okay, so have a look at this video here, please, and I'll see you on Thursday. And office hours are for an hour afterwards, except for today. I'll just keep it open for a little while longer. If nobody says anything, I'll just cut the meeting. Are my TAs here?
Yes, I'm here.
Well, you can introduce yourselves if you like.
Okay. Hi, I'm Fatima. I will be your TA this semester. I guess we're going to have a nice semester together. So that's it.
Great, excellent. And so they'll be sending out their, thank you, Fatima. We have two TAs. They'll both be sending their office hours. They have them already, and they'll just send them to you afterwards. They'll be, of course, Zoom office hours like this. And if there's no more questions, then thank you for all attending. Oh, God knows how many of you there are. I mean, it's topped out at 99. I've got the waiting list people here as well as the class and some extended invitations as well. Kirash, how'd that go for you?
Great so far. I mean, of course, I'm auditing the class, so
Well, then you can.
Looking forward to Thursday's class.
Excellent. Yes, when all things begin. All right, people. Thank you for attending. This was much more fun than 376 yesterday, let me tell you. Take care now.
Thank you.
All right, thank you very much.
Thank you, Stephen.
Cheers.
Thank you.
Thank you so much.
Bye bye.
Take care now.
Thank you.
Bye-bye.